So you want to integrate the other way. So for those who are joining now, I apologize for the abrupt beginning of this lecture. It did not start recording, so please watch section 1 if you want to see the entire lecture. I am doing a slightly different problem than was done in section 1. So just quickly review the only thing that was different so far is I've chosen the functions y equals e to the x from 1 to e, and y equals e squared x minus 1 over e minus 1 plus e x minus e over 1 minus e. And that's just the line connecting these 2 points. And this is held to be a region that's both horizontally and vertically simple. And if we do it first integrating with respect to y from fixing x, things are set up perfectly to do the integration because we've got y as a function of x. If you want to do it the other way, if you want to first fix y and do the x integration, then what we need to do is we need to rewrite things. We need to find the inverse functions. So some of them are easy, some of them are hard. And so we have 2 different curves. So for this one, if y equals e to the x, how would you write x as a function of y? It would just be natural log. And annoyingly in college, the way we write natural log is just you write log x. Sometimes we'll still write ln for natural log, but typically in college people write log. So the inverse function there is not so bad. So if you want, we can call this the right bound. R of x is log of x. The more interesting one is the other one. So we have here y is equal to e squared x minus 1 over e minus 1 plus e x minus e over 1 minus e. Okay. So we have y equals ax plus b for some a. Does everybody agree that there's some a and b that work? A would be e squared over e minus 1 plus e over 1 minus e. That would be the coefficient of x. The constant term b would be negative e squared over e minus 1 minus e squared over 1 minus e. Now, if you look at that, negative over 1 minus e, that's the same as negative e squared. Oh, sorry. Which is b. So what would be equal?
When you have to like combine it, so it's like only one term of x?
Right, and so I'm saying the coefficient of x is e squared over e minus 1 plus e over 1 minus e.
Oh, okay.
Right, that's the coefficient of x. The coefficient, the constant term, is going to be negative e squared over e minus 1 minus e squared over 1 minus e. How does b simplify? It's not so bad. I can move this negative down here and flip the order. What does b equal? 0. So here's my a, here's my b. I'm going to just consider the more general case of y plus ax plus b and just show you how you do the difference. So we want to solve for x as a function of y if y equals ax plus b. We want to do the general case of the line. For this particular problem, a is equal to this and b is equal to. Well, if y equals ax plus b, then ax equals y minus b, So x is y minus b divided by a. What's the only thing we have to be careful about? A is equal to 0. And so fortunately for us, a is not equal to 0. If a were to equal to 0, you have y equals a constant. And you should not be able to then invert this. So now we can set up our integration. So now, what we're going to do is we're going to be integrating this way. So we fix a y, and then we have x change. So y goes from the bottom, which is e, all the way up to e squared. And then x goes from the lower curve to the left curve to the right curve. So this is the R of typo. This should be x equals the log of y. Right? If y equals e to the x equals the log of y. So x equals the lower bound at y, or the left bound at y, to the right bound at y. Xy, dx dy. And that would be how you switch the orders of integration. Yes? So we just have this equation of a line. I just have to simplify the algebra. If you want me to write this out the long way, it's e squared over e minus 1x, right? Minus e squared over e minus 1. Then I have plus e x over 1 minus e minus e squared over 1 minus e. So I just group together the terms that have x. And you see, what is the coefficient of the terms with x? I have an e squared over e minus 1 times x. I have an e over 1 minus e times x. Well, I just add up these two things over here. I have a negative e squared over e minus 1. And I have a negative e squared over 1 minus e. These two things are opposite of each other. First, the denominator is multiplied by negative 1 through this. So when you do the algebra, they'll just cancel. So it turns out for this problem, b happens to be 0. I wanted to just do the more general. I could write b equals 0 and just do y over a. But I wanted to show you how to do the more general case of y. And then section 1 has a different example using the functions y equals x squared and y equals the square root of x. So if you want to see another example, section 1 video will give you another example. And now I just plug in what L of y is. So my lower bound is just log of y. And my upper bound is just y minus b over a. And that gives me my bounds of integration. And the hope is that one of these two will be doable. It is possible that neither one of them is doable and you'll have to do something else. But the hope is that one of the two regions will be known. Depending on what problem I give you, you might have a sense of what might be good. If I give you e to the u squared du, that's not a fun function to integrate. What do I want to have in front of the du that would make this nice? u. Because now the derivative of this is now set up to be the chain rule. If I wanted the antiderivative of that, that would just be e to the u squared, because the derivative of e to the u squared is just e to the u squared times 2u. So if I give you x e to the x squared y squared, I have to decide, do I want to integrate this with respect to x first or with respect to y? Well, if I multiply this by 2y and then divide by 2y, so 2y squared, this is now set up to be a nice integral with respect to x. And then maybe when I evaluate things, it will become nice, depending on what the bounds of integration are. Fortunately, there's only two options. You do x first and then y, or y first and then x. If one of them is not working, try the other. But that said, if you can look at it and try to figure out which is almost surely going to be the better one to look at, then I would do that one first. Okay. So there was a couple of questions on problem 37 from the homework. And so we had the function sine square root of xy, 0 less than equal to xy, less than equal to pi. And we wanted to bound the integral. We wanted to show using Riemann sums, x goes from 0 to pi, y goes from 0 to pi, sine square root of xy, dx dy, plus equal to pi squared. And what's nice about this is in the region that x and y go, the argument of sine is always between 0 and pi. And so if sine is taking, if I'm taking as input a number between 0 and pi, the sine is going to be between 0 and 1. So we know 0 less than equal to the sine of the square root of xy is less than equal to 1. So if I take my region of integration, and I break it up, for each one of these, I want to calculate my upper sum and my lower sum. So if all of these rectangles have the same area, I need to find an upper and a lower value of each one. Now, if I stay down here near 0, is the sine of the square root of xy going to be anywhere near 1? No. So using 1 as an upper bound is bad. Okay. You never said find a good upper bound, you said find an upper bound. So on each one of these, 0 is going to be the lower bound, 1 is going to be the upper bound for each one of these. And again, I can do better if I take into account where I am. But for each one of these, 0 is the lower bound and 1 is the upper bound. So the lower bound, because I have the same value 0 for every lower bound, it's just going to be 0 times the total area. If I had different bounds and different rectangles, then I would have to take each rectangle's area, multiply by the lower bound again. And that would give you a much better result. But here, what's the total area? So what's the area of this? Pi squared. So the lower bound is 0 times pi squared, which is 0. And the upper bound is 1 times pi squared, also known as pi. So that's where you get the bounds for this problem. These are not great bounds. These are basically, there's no shift bounds. The function is non-negative. It's at least 0, so the integral can't be negative. That's not a tremendous amount of information. The integrand is at most 1, so the value of the integral is most 1 times the area. So these are extremely weak bounds. If you want to figure out, what does the integral actually equal? In fact, since I am, so you can't see this now, but if you watch this at home later, I will integrate, I'll do numerical integrals, and I will do sine of square root of xy and I will do this, x goes from 0 to pi, y goes from 0 to pi, and I'll email you what the code is later. And if you numerically integrate, back in the wrong spot, if you numerically integrate, you get 7.407. So let's divide this by pi squared to put in perspective. It's about 0.755. So it's approximately approximately 3/4 pi squared. So it tells you it's not horrible bound, but I don't know where is it between 0 and pi squared. Yes. It's the area, it's the sum of the areas of each rectangle. So to calculate the lower bound, it should really be a sum over each square, or each rectangle of the lower bound value of the rectangle. But because they all are being zeros, I can just take that out and it's going to just be the sum of all the areas, which is pi squared. If instead I gave you something like this, where the lower bound is 1, 2, 3, and 4, then it would be 1 times the area of box 1 plus 2 times the area of box 2 plus 3 times the area of box 3 plus 4 times the area of box 2. And in each box is 1/4 the total area. It would then be 1 plus 2 plus 3 plus 4 times the total area over 4, which would just be 10/4. And so this would be a more interesting bound, where I'm now using some knowledge of the function. I'm using some knowledge of the function before with the square root of x, y, but not much. I'm not taking into account which box I'm in. I'm using the same thing for every single box. That's okay, but it's not surprising that it's not the best we can do. The more work we do, the better estimate we should be able to get. So I want to end with one last application of inverse functions. So inverse functions and chain. Assume we have two inverse functions. So a of x is f of g of x is x. Okay? Let's calculate a prime. If a of x is x, can somebody tell me what's the derivative? 1. But by the chain rule, it's f prime at g of x times g prime of x. So we can solve for g prime of x. So we get g prime of x is 1 over f prime of g of x if f and g are inverse. So this is an extremely useful result. If you know a function and you know its derivative, you actually know the derivative of its inverse. So let's do an example. Let's look at the tangent of the arctangent. So what does it mean to say the arctangent of x? It means I want the angle. Let's call the arctangent of x theta. I want the angle whose tangent is x. Tangent is opposite over adjacent. So if I want an angle whose tangent is x, let me draw a right triangle. I'll put an x here, and I'll put a 1 here. And then by Pythagoras, the hypotenuse would be 1 plus x squared square root. Now think about what I'm doing. The tangent of the angle whose tangent is x. What is the tangent of the angle whose tangent is x? X, you just listen to it. I'm taking the tangent of the angle whose tangent is x. If you take my tangent, you will get x. That's what happens when you take my tangent. So if I take the tangent of the angle whose tangent is x, you get x. Sometimes people write tangent inverse for arctangent. There's a lot of people who hate that notation because are you talking about the inverse tangent function or are you talking about 1 over the tangent? And so that's why a lot of us like to write arctangent. Well, we can now use this result over here, which we get arctangent prime of x is 1 over tangent prime at arctangent of x. Does anybody remember what is the derivative of tangent? Anybody remember? Secant squared. And you can remember this by, tangent is sine over cosine, so tangent sine, derivative of sine is cosine minus sine derivative of cosine minus sine over cosine squared, and it's 1 over cosine squared. So this is equal to secant squared. So the derivative of tangent is secant squared. We have 1 over secant squared, so this is the same as cosine squared of arctangent of x. Right, we now have the derivative of arctangent. It's the cosine square of arctangent of x. This should look like gobbledygook to you. So I have the derivative of arctangent, but it involves taking the cosine of the arctangent of x, and I don't really understand the arctangent. But I have my triangle. I'm asking for the cosine of the angle whose tangent is x. What's the cosine of this angle theta? Yeah, so for this problem, cosine of arctangent of x is just 1 over the square root of 1 plus x. So if I take the cosine squared, I have 1 over 1 plus x squared. That's arctangent times x. We now have an antiderivative of 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is just arctangent of x. Because if the derivative of arctangent is this, then the integral of this is arctangent. You can see differentiation and integration are kind of like inverse functions. Oh no. And I just realized the whole video has been, people at home, you should have yelled that I was not sharing the screen. That was only the numerical calculation. So, okay, so fortunately, this was done at the end of section 1, so this was a terribly recorded lecture in terms of structuring things. But fortunately, you can just watch most of section 1. This is the advantage of having things recorded twice. And then this was just going through and doing the inverse functions and seeing that we can use what we've done for one to get another. And so we can use this to find nice antiderivatives. 1 over 1 plus x squared. If we wanted to find the antiderivative of before, we would need x over 1 plus x squared. And then we could do like a u substitution. We can't do that, but fortunately by using the inverse functions and the chain rule together, everything works out. All right, have a good day. I'm going to just talk for like a minute or two, just to fix the recording for those who continue to watch. So what we did is we did the inverse functions in the chain rule. So if I give you a of x is f of g of x equals x, then a prime of x is just 1 from this. And then using the chain rule, it's going to be f prime of g of x times g prime. So solving for g prime, we get g prime of x is 1 over f prime of g of x. And so if f and g are inverses, we have a way to find the derivative of 1 if we know the other. So if we take the arctangent of x and we try to find its derivative, the tangent of arctangent of x is equal to x. The tangent of the angle whose tangent is x is x. So arctangent prime is 1 over tangent prime of arctangent of x. And we know that the derivative of tangent is secant squared, so 1 over secant squared is cosine squared. We look at our triangle, and if the angle has a tangent of x, the opposite is x, the adjacent is 1, the hypotenuse is the square root of 1 plus x squared. So we get the cosine of arctangent of x is 1 over the square root of 1 plus x squared. So the derivative of arctangent prime is just 1 over 1 plus x squared. And this has wonderful applications to finding a numerical value for pi. All right, have a great